You have just thrown a ball and it's travelling upwards. Neglecting air resistance, what force or forces are acting on the ball? A. The upward force from your hand. B. The downward force of gravity. Or C. Both of these. The answer is just the downward force of gravity, which gradually slows the ball, stops it, then brings it back down, making it fall faster and faster. Without gravity and air resistance, the ball would just go on travelling in the direction of your throw. Yes, the ball thrown up in the air comes back. Jump, and you're pulled back to the ground by gravity. Without the gravitational force, there would be no moons orbiting planets, no planets orbiting stars, and no stars held in galaxies. It's something we discover as babies, and we take it for granted. Famously, the concept of gravity was first proposed by Isaac Newton in the 1680s in his book Principia, which contained the universal law of gravitation. As the legend goes, he was sitting under an apple tree when an apple fell on his head, and he began wondering, what pulled it to the ground? Newton had the idea that gravity acted not just on apples, but also the sun, the moon, and the planets. The force increases as either or both of the masses m1 and m2 increase and drops off by the square of the distance r between them. So for example, doubling the mass of one of the objects also doubles the force of gravity experienced. But doubling the distance between the two objects results in the force being reduced to 1/4 of the original value. Gravity is an attractive force only and acts weaker over long distances. It's the gravitational force between the Earth and the Sun which keeps the Earth in orbit. Without this force, the Earth would continue to travel in a straight line. People often explain weightlessness in the space station as caused by the lack of gravity and talk of microgravity or zero gravity. But the space station is orbiting the Earth like the Earth orbits the Sun. It's the gravitational force between the Earth and the space station that keeps it, and all the objects in it, in Earth's orbit. If the space station were not moving, it would fall straight down towards the centre of the Earth. In an orbit, it is constantly in a free fall as it constantly bends round in its orbit. All the objects and people in the space station are falling together, and so relative to each other, they are weightless. You can try this at home. Put a feather on a coin in a transparent large plastic sweet jar and throw it upwards. The coin and the feather appear to float weightlessly inside the jar. This is just like the objects and people in the space station. It's only when you oppose gravity by holding the jar in your hand that the feather and the coin seem to have weight and settle to the bottom. We are weightless when we free fall, but gravity is acting all the time. It's not micro or zero gravity. On Earth, we think of gravity as being a constant. This is because the mass of an object and that of the planet beneath us is constant, and any change in distance between an object and the centre of the Earth is negligible. But the gravitational force isn't limited to huge objects like planets. There is an attractive gravitational force between any two objects. But with everyday objects, the force is far too small to notice. However, if these two were in outer space, far from any stars, and 10 meters apart, they would experience this tiny gravitational force that would cause them to accelerate towards each other. But it would take nearly 2 weeks before they collided. Albert Einstein's theory of general relativity was published in 1915. In it, he proposed that massive objects cause a distortion in space-time, which is felt as gravity. But this story is for another day.